Okay, number 4, another objective. I want you guys to be able to use story problems or real-world situations where exponential functions are used and be able to make predictions and be able to model it with a function. So suppose a bacteria population starts at 1150, and decreases at 5% a day. Write the function. So that objective here, using a real-world modeling problem like this, requires an accurate use of this formula over here. The spot where students tend to goof up a lot is this right in here, is handling that 1 and the plus and minus r. Remember, if your rate was going to increase, then you would be using the plus sign there, 1 plus your rate. And then or if it was decreasing, which it is in this case here, we want to use the minus sign. Just like so. Now, the other part where students really goof up is when you actually are dealing with those decrease situations there, and when we're decreasing at a rate of 5%, that number right here, that 5% needs to get inputted here. So don't forget about taking 1 and subtracting the 5%. And remember, you can't put a percent in there. It's got to be a decimal. Okay, so 5% as a decimal, 0.05. So now when we take 1 minus 0.05, that's going to give us our function here of our initial amount, which is 1,150, and then 0.95. Notice it's just 95% of what the previous value would be, and then we raise it to whatever variable you wanted there. In this case, if I use t here, I got to use t there, right? Now, how many days will there be fewer than 500 bacteria? Well, one approach would be to type that function into your graphing calculator. And then once you have the function typed into your graphing calculator, just travel over to your table, hit second graph, and then you're just playing the scrolling game until we reach a value that is under 500. Boom, there it was right there, 17 days. Alright, so after 17 days, that's when we will get fewer than 500 bacteria. Now, what about this bonus part here? Bonus if you can tell me the hours, the minutes, and the seconds. Well, somewhere between the 16th day and the 17th day, it got to exactly 500, right? I think that's fair to assume. So, at what point did it actually become 500? How can we nail that down? Well, let's go back to our graphing calculator. One approach that we can take with this thing here is we could look at the graph, and if you notice my graph, it doesn't show up. The reason why is because if you notice back when we looked at our table, I mean even right here at 17, when x is 17, our y value is 480. This up here is 10. So we need to adjust that window quite a bit. So if we hit our window feature here, hit second, actually not second window, just hit window, and we look at the y range here, we're going from -10 to 10. Well, we need a lot more than that. Remember, the starting value there was 1150. So let's make it go to, I don't know, 1200. Now let's hit graph. There we go, we can see it a little bit. Okay, so we want to know when this thing is 500, right? So when is that bacteria population going to hit 500? Let's go to our y equals, and let's just type in 500. Now hit graph. There's the 500 line. So our intersection value is somewhere out there, and we still can't see it yet. Let's adjust the window and give ourselves some more x's. We need some more runway here. So x max, let's make it go out to 20 instead of 10. Ah, there it is. So to find that intersection point, let's hit the second button, and let's hit trace to go to a calculate menu. Then hit 5 for intersection. First curve. It already has the first curve selected. Hit enter. Notice it automatically jumped to the second line, not curve. Hit enter, and then it says guess. Well, there's only one intersection point with this particular situation, so we don't really have to guess. The calculator will find it. And sure enough, there it is, 16.238168. So then what you'd have to do is copy down that number and then just start to work with that decimal there, because what that decimal is representing is the percentage of the 16th day. So using that percentage of the 16th day, we can then nail down the hours and minutes and seconds. That's the graphing way of approaching this problem. There is an algebraic way of approaching this problem, and let me show that to you now. So an alternative way of getting that value is we can just say, well, if this was our function, 1150 times 0.95 raised to the t power is going to be equal to, now we want to know when this is going to be 500 or less than 500, so let's just plug in a 500 right here. And now we're just going to solve this problem using a little bit of algebra. According to this problem here, the first thing we'd have to do using order of operations is take the 0.95 raised to the t power and then multiply by 1150. So when we solve, we have to do the reverse order of operations. So the first thing we're going to want to do is divide by 1150. Oops. Click, click. So then that divides out to be 1, giving us nothing more than 0.95 raised to the t power. And then the 500 divided by the 1150 gives us approximately about 0.435. Now, don't round that number. You're going to want that number later on, so leave that in your calculator. Don't hit the clear button. You're going to want that number, because the more you round a problem as you go through the steps, the less accurate your final answer is going to be. Alright, so what's our next move here? Without using a graphing calculator to get the intersection point, is that good old standby move that we looked at when we were solving in section 7.5. That's log, plug, and divide, right? Let's take the log of both sides. Okay, now that we took the log of both sides, that allows us to do the plug property, and that plug property allows us to take that t that is right there, and now that t can move right out in front. So now let's just do that. So now that the t is out in front, now our next move is going to be divide. And so now when we're talking about divide, our job here is to get the t here by itself. So to divide this thing, let's divide by the log of 0.95. Alright, so what's going to happen over here is those will cancel out, leaving you with good old t. And then over on the other side, this is why I had you guys leave that decimal there, and why it's a good idea to leave that exact decimal in your calculator. Because now from the calculator, we're going to take the log, hit log, and then hit second, and then your negative sign there to use the previous answer. Close the parenthesis. I can't stress that enough, or else it'll throw off your answer. And then let's divide that by the log of 0.95. That looks familiar, doesn't it? 16.238, and that's exactly what we had here, the 16.238. Okay, so there's another way to get that answer. Okay, great. So now to get the hours, minutes, and seconds, take off that 16, trim that off, so now we can just look at the percentage there. That's the percentage of the 16th day. So to figure out the number of hours, let's multiply that by 24. So 5 hours, trim off the 5. It's that percentage of an hour. So percentage of hour multiplied by 60. There we go. Trim off the 42, because it's that percentage of a minute. So let's multiply that by another 60. Oops, don't want that negative sign in there. Delete that. There we go. So, recapping all of our numbers here, I believe, wasn't it 5 hours? Yeah, so 5 hours, 42 minutes, and 58 seconds. Remember, at the 58th second, we are going to have that bacteria population be less than 500. So 17 days, 5 hours. Oh boy, I forgot the time. I forgot the number of minutes. Oh yeah, 42 minutes and 58 seconds. Hey, I'm out of the way. All right. These next few problems, number 5, there's a couple different ways you can do some of these ones. Letter A there, those are those problems that it is possible to do mentally. So the mental arithmetic behind these things is having, once again, a very clear understanding of the conversion of a logarithm to an exponential equation. So here, if the base 3 log of 81 is some value, some unknown, then that's really saying 3 to what unknown value would be 81. So mentally we could figure that out, guessing and checking. But I'm pretty sure that's 4, right? 3 to the 4th power is 81. Notice we really can't do the same thing here. 7 to, I don't know, it's going to give us 58. So we need to have a way of doing this. So once again with our calculators, one approach would be using the updated operating system's cool new feature, hitting the alpha and then the window button, and then we select number 5. And so we were doing the base 7 log of, was it 84? Oh no, it was 58. So 5, 8. Enter. There we go. Round these to 3 decimal places, please. Awesome. Next one. That's pure calculator work right there, folks, isn't it? Just a reminder, though, that's just an invisible base there of e. And if we're trying to figure this thing out, e to, I have no idea what power it's going to take to get us 77. So we just make the calculator do that for us. Do that. Natural log of 77. 4.349, right? Nearest thousandth. Oh, I'm sorry, 4.344, right? That 8 right there rounds it up to a 4. Alright, the next one, the natural log of e raised to 2x. Wait a second, what makes this one different? Every single one of the previous problems, there was no variables. Now there's a variable, so what gives? Well, we got to remember here on these problems that underneath it all, we have an invisible e right there, right? So if we have the natural log base e of e raised to the 2x, and we're trying to figure out just what that's equal to, remember, rewriting this, we have e raised to some unknown power is going to be equal to e to the 2x power, right? Because this whole thing right here, what we can kind of picture that whole thing being is just this a value right here. So when we rewrite that, that whole a value moves over here. So doesn't that mean that this answer right here is nothing more than just 2x? Okay. It's also very similar to this property. Where did it go? Oh. Ah, there it is. Is that when you have a natural a log where the base is the same, the answer is staring you right in the face. Better yet, it's actually more like this one right here, wasn't it? Where the log, same base, that base to the power, the answer is just the power. So looking back up here, notice the power there was just 2x. Okay, let's keep on moving this thing along here. Single logarithm, you guys did an excellent job with this. Just a reminder that when you have an addition sign between the 2 logarithms, the property that we can use here is we can take the 2 values here and just multiply them together. So now to write as a single logarithm, log base 6, 30 times 7.2, 216. So that's that part. So then all we've done so far is we've expressed it as a single logarithm. The next thing we have to do is evaluate it. So sometimes you're going to run across situations like these where you can just figure it out on your own. Pretty sure that 6 to the 3rd power is going to give us 216. Okay, so if we look at the next one here, now that we have a subtraction sign going on in here, now that tells us we need to take the 512 and the 8 and we have to divide them. So that means we'll have the base 2 log of 512 divided by 8, which is 64. 2 to what power gives us 64? I'm pretty sure that's a 6. Let's just double check though. Yep, there we go.